Smooth is very curious because the set of numbers having small prime factor are not smooth at all. Tenenbaum called them friable, but this is not really very good terminology, so I don't know. I keep smooth and round. Okay, so I introduce the two functions, one which is the indicator of numbers having small prime factor and the other having large prime factors. Okay. I will use this in different situation, two at least, and I just bring your attention that as a convolution, this is just one. That means that you can split the integers in two parts. Product of primes less than 1, product of prime bigger than 1. So that's the first convolutional relation you see. From it you can deduce by Montgomery inversion formula that the UZ has a mean value which is equal to what is written there, product of B less than Z, 1 minus 1 over B. Okay. The first proof, the first application of this would be on the prime number theorem. Many of you know that it is equivalent to the fact that the Mobius function has been value 0. I will discuss the lemma 5, which gives an upper bound on the sum for all multiplicative functions bounded by 1, using only smooth numbers. There is some very curious fact here. The left-hand side of this formula tends to is decreasing, so it has a limit as a positive number decreasing. It has a limit, and all the stuff will be to show that the limit is 0. But we know that there is a limit of this thing. The second thing here, this is a really sharp inequality. It is easy to get this inequality. It's not a really complicated thing. It is like hyperbola method. You can't. You make some subdivision on the integers when you apply the convolution relation, and you get this thing. So it's not really deep. Anyway, if you take f of n equal 1, you get in both sides 1. So that means it's in some sense sharp. Moreover, take f of n equal uz of n. Then on the left-hand side, you have vzn uz of n, and this is 0 and this n equal 1. So you get 1 over the 1 multiplied by the product. And this is exactly the truth. This is the limit with the limit of uz of n. So this is inequality. This inequality is really a very useful inequality for all multiplicative functions. From this, how can one deduce the prime number theorem? There is a problem with this, maybe I return to this. The integral is from 1 to infinity. If you can get it, and that will be the second lemma, from 1 to z, then we can get rid of the vz of n, and we'll have an average of the function on some set. We attain this by the lemma 6. The lemma 6 that we can get rid of the part from z to infinity in the integral. It is bounded by beta c minus 1 plus c is e to the gamma or something, or e minus gamma. I never will be able to remember which one of them. But call it just c. It is the constant which appears in Merton's formula. So we can get rid of the z of the integral, the part of the integral which is bigger than z, and we are left to an inequality which is really important in this field, that we have a lim soup which is dominated by an average of this mean value. And if the limit soup is dominated, you can think that it has a limit. And if you just say mu of n, the mean value of mu of n exists, you prove the prime number theorem. So it is a very delicate thing. Just assuming that mu of n has mean value, then you can show that the mean value is 0, necessarily, and you get the prime number theorem. Okay? So, so we have here, for the Mobius function, we shall use some known fact about the Mobius function, that the sum mu of n over n is less than equal 1, and or any constant. And from this, by classical Tuberian argument, we can prove that the limit of mu of n is 0. And we get the prime number theorem. So the prime number theorem comes really by studying by using the first inequality of the lemma 5, which is really very easy to obtain. It's not a deep thing, it is just a kind of high-parabola method. Okay. This is valid for all multiplicative functions, as I said before. So we can use this to obtain Euler's theorem. Of course, the weak form of Euler's theorem. Tenenbaum talk about a deep form of Euler's theorem with error terms. Here there is no error term. It's just qualitative things. And it is really easy because we can show that there is equality between the lim soup and the limit of the integral from 0 to infinity, 0 to omega, a of t of t. It's really curious here. I cannot read what is written on this stuff. Doesn't matter. Okay, so we can obtain this just by Parseller formula as usual, connecting this to the Dirichlet series associated to the multiplicative function. Okay. There is another type of example I want to show, applying now rough numbers. And this comes from when you are working with the exponential sum over primes. We learned from Vinogradov, and for me, I learned it from Bob Vaughan report on Mittag-Leffler conference many, many years ago, that we can deal with sums of two types. The sum of type 1 and sum of type 2. The sum of type 1, in front of the exponential, we have just 1. In sum of type 2, which is just applying Cauchy-Schwarz inequality and getting the sum of type 1, we need that the sum must be, one of the sum must be large and not too small. So we have, not too small and not too large, both things. There must be some equilibrium. Is it correct? Equilibrium in English? Okay. Equilibrium between this stuff. Okay. So there is one way to get an identity of one type, and I want to insist on this because it is really, really easy and normal to think about it. Okay. The second. This page says that just I can ignore some of the primes less than z, which is not a problem. So we start from the relation that the log is lambda star 1, which means that only log n is the sum of the primes composing n. Okay? This is multiply by uz. Uz is the indicator of rough numbers. You get immediately a sum of type of one type. So it is easy to remember. You start from log is lambda star 1, you multiply by uz, and you have another identity. Okay? Well, the other lines explain how this is exactly a sum of type 1 and sum of 2. Well, you can see at the end of this thing that it is really a balanced function. We have n is bigger than z and less than x over z. So we have a balanced form of a bilinear form. We have also a factor which is uz of n log n, which by partial summation gives a sum of type 1 almost. We have just to restrict somehow and apply a trivial estimate for the last range, m bigger than x over z and less than x. This gives a following type of result, that the sum of a over q is less than x log 3 over quarter. And 3 over quarter is important because it's less than 2. And 2 is as I said before, this is there is an effective result on prime in arithmetic regression due to Page and Landau, Page, and so on, and which is valid only for q less than log x to the 2 minus epsilon. We have nothing beyond q bigger than log x to the log x to any power, because there is some Ziegler zeros which may appear, and this is non-effective. So this range is very interesting. The identity itself saves just some few factors of logarithm on one identity, which you just say 2 of a factor log x to the 2. Okay, and this enables us to get the 3 over 4. I give an example of an estimate to be obtained by this method with very explicit, everything is explicit here. And this was, at that time, we want to improve on some result of Chen, who wrote some things about exponential sum over primes, and we have better estimate. There is another thing to do with this identity. It is just to apply some sieve result. uz is a sieve function. So we can apply what is called the fundamental lemma of sieve to estimate everything on the identity I wrote about. And you have the details in this page. I will not repeat it because it is, well, it's technical stuff. But we have exactly, we can obtain everything, we can estimate every terms just by using C. This leads to an estimate which is good enough to say that the following result occurs. For any irrational number, the sequence P alpha is distributed modulo 1, and this doesn't use Dirichlet series, it doesn't use prime number theorem, just Chebyshev estimate. Okay. We can obtain the distribution modulo 1 of the set P alpha just by using Chebyshev estimate, which is the order of magnitude of the lambda of one called mean value. And all the others comes from seed technique. Okay, I was a little bit on time, so I didn't get Harold having more time.
Questions, remarks? In that last slide, is it an effective result?
Everything is effective. Everything is effective when you apply the sieve, the sieve technique. Everything is effective.
There's nothing to do wrong.
Yeah. it is explicitly.
Yeah, that's very nice actually. Very good. Okay. Other questions, remarks?
Thanks. What is what I would say? Krishna, happy birthday. No, he explains to me that he has people from the staff. Okay.
Well,
thank you.
Thank you.